Welcome, everyone, to this week's episode of Planarly's tutorial. Planarly is my Ep4 GPL-licensed open-source research project to explore the potential of spreadsheets as a general-purpose two-dimensional programming environment. Planarly takes a conventional spreadsheet user and gently introduces proper programming habits and more advanced topics in the familiar context of spreadsheets and cells. In the last video, we looked at turning sheets into functions. We focused on the simple case where the input parameters and output return value are all single cells. Today, we look at the more complex scenario where the inputs and outputs are tables. Let's build a sheet as function named summary. Given a table x0 to zx0, we return the sum, the number of elements, and their average as a struct. Notice the result of a division is always a floating point number, hence 3.0 instead of just 3. Me with a capital M is a reserved word denoting the current cell, and caret caret is the move up operator. The hash return region defines the return value. Now, in the main sheet, we can call p.summary with the table 1 above 2. Wow, it worked. We can also address the individual fields of the struct using the square bracket operator. But what exactly happened here? Why can we substitute a region of cells with something of a different size? When passing a parameter x0 to function summary, Planarly does three things in the overlay: the set of hypothetical substitutions implied by a function call. 1. It removes the hard-coded values in the x0 region. 2. It removes the label zx0 if defined, so that the x0 region is reset to a clean slate. 3. It replaces the content of cell x0 with the value passed in this case, 1 above 2. Recall that zx0 defaults to the end of the spill area of x0, so here. The hash return region now contains the correct return value, as expected. The astute reader would notice that the function does not work correctly for a multi-column table. The formula count equals height x0 assumes a single column. In addition, a wide enough x0 would conflict with the return cells. Let's see what happens when we pass in a multi-column table anyway. We get an error. A single column is expected. This is good, but how does Planarly know it's an error? The reason is the parameter shape compatibility rule in Planarly. The passed-in value of a parameter must be shape compatible with its value in the implementing sheet. In this case, since x0 is a single column in the implementing sheet, the passed-in value must be a single cell or a single column. 4 different shapes are recognized in Planarly: a single cell, a single row, a single column, and a multi-row, multi-column proper table. If a sheet is designed with only single-cell parameters in mind, like the square function in our last tutorial, then only single-cell values are permitted. If we wish to allow the summary function to operate on proper tables, its x0 must be a proper table. Let's make it so. It's now obvious that the count formula is wrong. We're programming by example here. The implementation itself is also a demo, where every parameter must take on its most general shape due to the shape compatibility rule. We fix the formula and add a barrier to prevent potential spill conflicts. And voila, the call works as expected. The input region indeed sums to 10, has 4 cells, and averages to 2.5. Let's see another example. This time, the input is so wide that without the barrier, the summary sheet's x0 region would have conflicted with the return region. And yes, the average of these numbers is 3.0. No conflict reported thanks to the barrier that we put in place. One last example, a wide proper table. The empty cells are treated as zeros, and this region of 10 cells averages to 2.1. No problem. In this tutorial, we learned how parameter passing works for tables in Planarly, and how the parameter shape compatibility rule protects sheets not designed explicitly to take arbitrarily shaped parameters. I hope you liked the ideas in this video. Check out our website, planarly.com, where you can try Planarly in Chrome. The application runs entirely in your browser, your data never leaves your computer. In next week's video, we will talk about table comprehension, the analog of loops in conventional programming. Follow me on Twitter, Dr. Planar, and see you next time.